Greetings to all. The session is regarding intermediate chemistry. This is fetching for the international entrance and competitive exams as well. India is conducting JEE Advanced, JEE Mains examination twice a year for IIT and NIT admissions. NEET exam will be conducted across India for medical entrance examination. Telangana and Andhra Pradesh government are conducting MSET examination for BTech entrance. So that is also technical domain. In addition, government organizations are conducting job opportunities, government jobs with the different criteria, different kind of subjects will be provided among all. General studies will be the common question paper assigned for all the aspirants. In that, general science content will be there. The content what we are discussing now will be helpful for your preparation. Let's go with the preparation and presentation for this intermediate level chemistry, right? In the question number 1, we will go with the Nobel Prize in Chemistry 2021 was awarded jointly to Benjamin List and David W.C. Macmillan for the development of asymmetric organocatalysis, right? Here, the Nobel Prize in the chemistry in the year 2021 is jointly awarded for the scientist Benjamin List and David W.C. Macmillan. And what are their contributions? They developed asymmetric organocatalysis. They focused on the catalysis method, and that is the kind of asymmetric organocatalysis. For this kind of exploration, research endeavors, they got awarded with the prestigious Nobel Prize in the field of chemistry. And these two are the scientists together received the Nobel Prize for the year 2021, Benjamin List and David W.C. Macmillan. So Nobel Prize receivers for the year 2021. Many industries, fields, wherever research, all the chemists are mainly depends upon the new and functional molecules. This could be anything from the substance capturing light in the solar cells, store energy in the batteries, and molecule that make lightweight running shoes, inhibit the progress of disease in the body, right? So here, this is the kind of applications of the molecules. New and functional molecules are to be introduced, and with the implementation of solar cells, we are able to utilize so many battery driven gadgets so that they are helpful, they are applicable in our day-to-day life applications. However, if we compare nature's ability to build chemical creations with our own, we were long stuck in the Stone Age. Okay, whatever reactions are carried in the nature, if we go with them only, what happens? The process whatever carried in the slow manner, so that we will still be in the age of Stone Age. Stone Age is the early civilization we can notice. So as the technology, as the scientific perception is evaluated, we are running through the various evaluations, various advancement, various progress. We can notice this is the prehistoric time, we can say. Evolution has produced incredibly specific tools, enzymes, and constructing molecular complexes, giving life its shapes, colors, functions. Okay, so many kind of new inventions got introduced into the daily life, so that our life is becoming so easy and convenient, in order to make the things in a span of time, blink of time, you are able to do the things. Maximum extent of things are able to completed, so that we can say now we are so much advanced in terms of technology, in terms of scientific methods, in terms of application of tools in every aspect, and application of the enzymes and catalyst as well, so that fastening of research is possible. This is the way we are being a human civilization is most intelligent among all the creatures which ever present. That's the reason why this civilization is distinct in comparison to all the living organisms. We can clearly notice that whatever organisms are there, so many millions of organisms we can notice in our what entire universe. But among all highly civilized living organism is the human only, because his ability to think, his ability to advance, explore everything is multi proportional advanced in comparison to all the remaining organisms. That's the reason why human being can do able to do so many things and in order to get the protection, in order to go for the exploration for the things. In every field we have such kind of distinct perception, distinct criteria in comparison to remaining all organisms. That is purely because of advancement in the various field. In that context, here the development of catalyst for fastening the rate of reaction also plays a role in this kind of advancement. Okay, when chemists isolated these chemical masterpieces, they just looked at them in admiration. Okay, whatever new invention is coming out, which is becoming a masterpiece in that, so that is a kind of admiration for so many people, and a new zeal will come in order to get so many such kind of things in the near future. The hammers and chisels in their own toolbox for the molecular construction were blunt, unreliable. So here whatever things we are using, that should be in a quick way of synthesis is required, and within the short time high yield of product and high quality product is required to be generated. So that should be in comparison to the nature's product as well. So this is the way so many criteria plays a role in order to get the advancement in the field of chemistry, right? New tools for the finer chemistry. Each new tool that chemists have added to their toolbox has increased the precision of their molecular constructions. Every day, the lot of research is going on all across the world. New compounds are adding to the research, we can say, entire research history. Every day, new compounds will be added because research and thinking till which the thinking process is endless, and that way the research is also going on always. It is seamless and endless as well, because no people are having boundaries in order to suppress that kind of zeal to go for a new thing. Every time we will go for a new thing, that should be applicable as well, so that a toolbox of chemistry is having so many weapons, so many kind of instruments over there in order to move forward with the high quality chemical reactions. Slowly but surely, chemistry has progressed from chiseling in a stone to something more like a craftsmanship. Okay, Stone Age, there is a kind of unfinished things we can notice whenever we are going for archaeological findings. Whatever things they used at the time, and if you are going to compare with the present day equipments, you can go with the so many drastic changes, so that we can say there is also the kind of same kind of morpholization, or else modernization, we can say, coming from the Stone Age to the craftsmanship. So there is a kind of professionalism everywhere. In every aspect, we can notice being globalization, interconnected, all the knowledge sharing ability. That's the reason why there is a kind of advancement we can notice. This has been a great benefit to humanity, and several these tools rewarded Nobel Prize in the field of chemistry, right? So these are few of the examples related with chemical auxiliaries, which are very much helpful. S limonene and R limonene, you can notice over there. Catalyst accelerate the chemical reaction. So the role of catalyst is that is most precious in the field of chemical research, we can say, or else already established a kind of reaction also. In order to proceed in the industrial scale quantity, uh, um, what introduction of catalyst is more important, because in the presence of catalyst only so many things we can introduce into the reaction. The first thing is we can speed up the reaction. If the reaction is proceeded for the 2 days in general without any catalytic method, so general completion of the reaction required for 2 days. By the addition of catalyst within short span of time, in the laboratory time equipments only, you can finish up either 1 hour, 2 hours. That depends upon the nature of the compound. First thing, speed up the reaction. And second is, so if you are going to set up the entire reaction, after the completion you may achieve more than one product as well. Whatever product you are expecting, along with that another unwanted products may be possible. If you are applying the catalyst, that will move on with a specific path of the reaction, so that undesirable products will be cut down, so that whatever product you are expecting, that will be elevated in the higher quantity. so that quality of the product will be enhanced. That is the second application of the catalyst. And moreover, catalyst, if used, drastic reaction conditions are not required. Heating at the higher temperature, extremely longer temperature, larger temperature for longer time, and high pressure application, that those kind of things can be optimized. Those will become mild conditions rather than extremely higher conditions, so that catalyst able to optimize reaction environment, reaction product, reaction time. So many conditions can be optimized by means of this catalyst, so that catalyst plays a vital role over there. In this regard, in 1835, renowned Swedish chemist Jacob Berzelius. So Berzelius is a familiar scientist in the field of chemistry, started to see the pattern in this. So what is the role of catalyst? How specific it will be in order to drive the chemical reaction? The entire analysis was carried by the scientist called Berzelius in the year 1835. In the Royal Swedish Academy of Sciences annual report describing latest progress in the physics and chemistry, he writes about the force that can generate the chemical activity, how the chemical activity is accelerating the reactions. That kind of study was carried by him. He listed several examples in which just the presence of substance started a chemical reaction, starting how this phenomenon appeared to be considerably more common than was previously thought. Okay, so whatever reaction we are progressing or we are proceeding with, that is becoming most common type of reaction. Earlier it was very hard, very difficult to achieve. Those reactions are most commonly observed nowadays. That is purely because of research advancement. He believed that substance has a catalytic force called the phenomenon itself catalysis, right? Whenever any complicated reaction, so many stepwise synthesis, so around 5 to 6 steps required in order to achieve the product, or else so many days required in order to achieve the product, or else a bulk quantity of reactants to be taken, so that poor yield you are achieving. These many kind of threats you can notice whenever you are starting, you are planning for any reaction. But when we are introducing a pinch of catalyst in that, entire threats, entire whatever problems we are, hurdles we are facing, so everything will be vanished. Rather, we can extract the product in the high yield. That is the role of catalyst in the entire field of chemical research and laboratory field. Catalyst produce plastic, perfume, flavors, food, everything. In every field we can apply the catalyst. So plastic industry, everybody aware nowadays, the application of plastics are most vital everywhere. We are applying in the household purpose, electrical field, automobile industry, aviation purpose. Wherever you see, everywhere the application of plastic is becoming most common, right? So it is the part of daily life. So that in that plastic heavy molecular weight substances, application of the catalyst is most important, because in order to synthesize that much of lengthy polymeric materials, catalyst application is most crucial. And even in the perfume industry, if you are producing the food, so many flavors of food we are synthesizing now, so at that field also the role of catalyst is more prominent. A great deal of water has run through the chemist, but since Berzelius time, they have discovered multitude of catalysts that can break down molecules or join them together. So any kind of molecule, whatever the complicated molecule it might be, by the application of water we can that larger molecule can be made into a small pieces, or else in order to combine the small molecules into a big one, in that also water plays a vital, being water is a universal solvent, right? So this is the way the reaction methodology, reaction pathway is required based on our schematic representation. So thanks to those, they can now carve our thousands of different substances we use in our everyday life, such as pharmaceuticals, plastics, perfumes, food flavorings. In fact, it is estimated that 35% of the world's total GDP in some way involves the chemical catalyst, right? So that extent it is most crucial even in the gross domestic product of the entire world. So in that 35% contribution is laying in the field of chemical catalysis only. because in every field the application of catalyst plays a vital role. That might be a industry, that might be a food processing device, that might be a polymer synthesis, that might be a pharmaceutical. Everywhere, in order to fasten the reaction, here the addition of catalyst is more preferential. That's the reason why. So its application, its presence is also the part of this gross domestic product. So this is not the small amount. So this extent importance catalyst is having, right? Life's catalyst works with the astounding precision. A second form of catalyst is compressed of the proteins known as enzymes. So in our human body, all the living organisms are secreting enzymes. Let me take the human body as a specimen in order to explain the role of enzymes over here. So many enzymes are secreted in the human body in order to go for the harmonical balance of entire metabolic activities of the uh, glands and also hormone secretion everywhere, right? Enzyme plays a vital role in order to digest the food, in order to transport, in order to generate the energy. Everywhere the use of enzymes are most crucial, because whatever food we are consuming, that is not entirely, so consumed food is not directly useful for your application of the work, right? So from that taking of food to the application into the work, so there are so many series of reactions. In order to make all these series of reactions, secretion of enzymes are most important. Enzymes are said to be biocatalyst. In our body, we are secreting these enzymes in order to fasten the reactions. Okay, so that extent biocatalysts are synthesized in the human body, so that we are fastly doing the all the works without any delay, right? So here these are said to be, enzymes are said to be life's catalyst, right? So if these catalyst fail, if these catalyst fails to work, so that our entire organisms are not working in a proper way, so that everywhere jam, so there is a traffic jam will be possible, so that works may not be done in a proper way. So biocatalyst called enzymes, or life's catalyst called enzymes, are most prominent in a living organism. This is the way the role of catalyst can be explained. Let me give the simplest example. Our digestion is possible or carried within 2 to 3 hours. Healthy human able to digest his food whatever he consumed, right? So that is the natural phenomenon. But if we are removing the catalyst hydrochloric acid in the digestive system, it requires 60 years for the complete digestion of the food. Around 60 years it consumes without hydrochloric acid. Being hydrochloric acid is the kind of enzyme, is a kind of catalyst in the digestive system, which used to fasten the digestion process. So that it is the role of catalyst, I would like to stress upon, right? So chemical reactions necessary for the survival of life. Many enzymes are specialists in asymmetric catalysis. Asymmetric catalysis is a specific focus in order to accord the Nobel Prize in this field in the year 2021. In principle, always form one mirror image out of two that are possible, right? So here asymmetric catalysis said to be whatever starting material you are taking upon addition of catalyst, so this starting material can be converted into a mixture of two products after the reaction instead of one. So mixture of two products, being it is a kind of asymmetry. Asymmetric means what chirality plays a role over there, and those compounds are having a different physiological activities. One of the compound will more potent, another compound is required in another field, that way. So here asymmetric catalysis we are discussing about. In this way they can build complicated molecules, amazing precision, such as cholesterol, chlorophyll, toxin called strychnine, which is one of the most complex molecules we know of. Everybody aware cholesterol is a very large sized molecule, and chlorophyll is also the biomolecule which exists in a plant material. Chlorophyll is only the green color pigment which imparts the imparts the green color, and that is only responsible for the food generation by plant materials, the process called photosynthesis. And here strychnine in either biomolecule, we can say. So these many compounds, in order to build these many compounds in the laboratory with amazing precision, the introduction of these catalysts are most important, right? So though they are available in the nature, but in the same way we are able to synthesize these compound in our laboratory in order to make more advancement in the field of research and science, right? This is the way the effect of catalyst will be there, and that part are taken care by the scientist Benjamin List and David W.C. Macmillan. Those two explorated especially the asymmetric organocatalysis process, so that new auxiliaries will be introduced into the field of chemistry, so that they can be exploited for the pharmaceutical advancement in the near future. So this is a kind of milestone in the field of chemistry, we can say, because the catalyst plays a role in order to go for the new way of synthesis. Though the starting materials and products are same, but new way of synthesis is possible by this asymmetric organocatalysis process. That significant it is, so that they are accorded with the Nobel Prize for their catalytic activity, for their outstanding contribution for this kind of organic research. Move on to question number 2. Question number 2 collected from Cambridge Assessment International Education. Here are the melting points and boiling points of the chlorine and potassium chloride are shown in the table. Chlorine is accorded with the melting point in the degree centigrade minus 101, and boiling point in degree centigrade is accorded with minus 35. Potassium chloride is given with melting point 770 degrees centigrade. Boiling point of potassium chloride is 1500 degrees centigrade. This is the data provided already. This numerical data is with you. Deduce the physical state of chlorine at minus 75 degrees centigrade. Use the data in the table to explain your answer. What is the physical state? What is your explanation, right? Here is the question is provided. If you are staying at the temperature of minus 75 degrees centigrade, at the minus 75 degrees centigrade, what will be the condition of this chlorine? Okay, so before explaining this question, what they are asking, first of all, we will see in general, in nature, what is the composition of chlorine, what is the physical state of chlorine in general, and what about potassium chloride we will discuss. Chlorine generally, it is the kind of gaseous component everybody aware about. It is the kind of covalent molecule, and both the chlorines are joined, being its atomic number 17, both the atoms are joined by the covalent bond in order to reach out that nearby organ noble gas configuration, and it is the simplest gaseous compound, right? So here melting point is at minus 101 degrees centigrade. If you are reducing the temperature to cryolytic region, where minus 101 degrees centigrade is extremely lower temperature, we can say negative temperatures. At this minus 101 degrees centigrade, solid chlorine will be converted into liquid chlorine. And whenever this chlorine is taken at the temperature minus 35, liquid chlorine can be converted into a boiled chlorine, means a gaseous chlorine one. Okay, so this indicates that above minus 35 degrees centigrade, chlorine exists in the form of gas only, right? That means above 0 degrees at normal room temperature is around 25 degrees centigrade in general, we can consider. At the room temperature, generally chlorine is the gas, because above 135 only chlorine is the gas, no? They are saying minus 75 degrees. Here, at up to minus 101, it will be a solid. It will be a solid chlorine. So when we are reaching minus 75 degrees centigrade, it will be a liquid compound. You can say this is a liquid one. And up to this minus 35, it is the liquid component only. If you're moving beyond this minus 35 degrees centigrade, it is becoming a gaseous one. So this is the way you can go for the physical state of the chlorine at minus 75 degrees centigrade will be the liquid compound. Liquid compound practically this temperature to be generated not available in nature. When you are creating this temperature, then only chlorine liquid you can achieve. So this is the question they are asking, and that correct answer will be a liquid one. And the explanation is being melting point is minus 101, below minus 101 solid only, above minus 35 liquid, so what gaseous component only. In between minus 101 to minus 35 it will be the liquid compound long range, you can notice. So this minus 75 is laying in between only, so that we can say it is the liquid. This is the proper explanation. In order to go for the more information regarding chlorine, chlorine is symbolized with the Cl, and atomic number is accorded as 17. Atomic mass is 35.45 atomic mass units. Melting point melts at 100 degrees centigrade at minus. We have to remember minus 100.98, nothing but 101 only. Then boils at minus 34.6. You can round up as 35, minus 35. Number of protons or electrons are 17, being it is a neutral. Number of neutrons are 18. Somewhat neutron count is higher in comparison to the proton count. And green color gaseous substance it will be. This is the way the chlorine data is provided to you, but the required answer is at minus 75 degrees centigrade, chlorine is existing as a gaseous compound. Move on to question number 3. Question number 3 is collected from 2017 paper 2 question. It will be, so this is the data provided to you. From this data, you can answer question number 34, 35 and 36 together. This is the data which is required for multiple questions. Okay. For the synthesis of benzoic acid, the only correct combination is. So here one of the starting material you can notice. This is the reagent you can notice. This is the process you're applying. So 3 columns are provided to you. What is the starting material is symbolizing the column 1. Column 2 is mentioned with the different reagents. Column 3 you can go for the path in which reaction will be proceeded, right? So the question is the synthesis of benzoic acid, the correct combination. In order to make the benzoic acid from this pathway, what process we need to go for? So the correct answer is 2,1-S. What is 2? Acetophenone can be taken. So 2 will be acetophenone. Acetophenone is benzene with the C double bond O CH3 is called acetophenone. That acetophenone can be treated with water reagent, sodium hydroxide bromine. Sodium hydroxide bromine is called Hofmann hypobromite reaction. It is the named reaction you can notice. So that acetophenone participate in the Hofmann hypobromite, and this is a haloform reaction we can say. Okay, sodium hydroxide bromination, this is the kind of haloform reaction. Whenever haloform reaction is specific for what? Methyl ketones only. The reaction is more specific for methyl ketones. So that haloform reaction if performed, that methyl ketone will be broken and that will be converted into C double bond Y is converted into COOH, and also you can achieve bromoform. CHBr3 will be generated, which is the entire reaction, so that you can synthesize the benzoic acid. So one of the product is benzoic acid, one of the byproduct is CHBr3, right? So the option D is the correct explanation. Reactant is acetophenone, sodium hydroxide, bromine are treated over. Bromine under alkaline conditions, we can say this reaction is said to be haloform. So this is a clear description for the chemical transformation. This is called acetophenone, where benzene is having C double bond with CH3. You can treat with sodium hydroxide and bromine as the reagent. Whenever sodium hydroxide bromine is treated, the entire methyl ketone, this is called methyl ketone, the bond will be broken in between, and this oxygen will be added over here, ONA is added over, and whatever CH3 is there, that will be turned into CHBr3. Bromine will be substituted over there. So CHBr3 will be precipitated, and sodium benzoate is generated, which is called haloform reaction. This is the way the question 34 can be answered, and the same data we can utilize for another question as well. The only correct combination in which reaction proceeds through the radical mechanism. Free radical reactions are said to be two types. One is called homolytic fission, giving rise to the free radicals, or else heterolytic fission, giving rise to the ions. Either cation or anion is used to initiate the reaction. The thing they are asking about free radical mechanism, in order to go for the free radical mechanism, certain conditions are specific. 1, 2 r is the required conditions here. Let's see. Okay, one is nothing but toluene. Toluene is said to be benzene which is containing methyl, which is called a toluene. Bromine, HNu. Wherever HNu conditions are there, HNu denotes photolytic conditions. Whenever photolytic conditions are applied upon any starting material, photolytic conditions mostly concerted and moreover proceeded with the free radical mechanism only, so that you can achieve the condensation, carboxylation, substitution, haloform. What you can say, substitution reaction will be proceeded, so that R. So here toluene is the starting material, bromine HNu is the reagent you can apply, and the substitution is the process by which the reaction will be proceeded. Okay. So in order to explain this one, let's see the path of chemical reaction. The chemical reaction is provided. Toluene is chemically demonstrated as a CH3 which is attached to the benzene ring. This is called a toluene. Bromine HNu conditions, if applied, the CH3 is turned into CH2 and one of the hydrogen replaced with bromine. So this is called benzyl bromide. Actually, everybody know that whenever bromination carried on toluene or any benzene related compounds, bromine will be attached at ortho or para or meta position. That is the kind of electrophilic substitution we can say. That is the case where we are applying the Lewis acid, AlCl3. If applied, then the substitution of bromine will be carried on the benzene ring. But the case is different. Bromine is required to be added in the presence of HNu. HNu is called photolytic condition. This photolytic condition always generate the free radicals which used to substitute the hydrogen with the bromine over there, so that we will get CH3 now turned into CH2Br. This is called free radical substitution reaction, right? So free radical substitution reaction is possible. And we moved on to for question number 4, 1, 2, and R are the correct answers. We moved on to question number 5. This is collected from Telangana MSET 2022 question paper. And this is the data. Metal sulfide is provided to you and the solubility product needed to be calculated. Here, there is no other way to go for the calculation. Rather, it is the statistical data, so that you can go for the comparison only. So what is the compound and what is its subsequent value, because it is not it is already existing in the table, so that it not required to be calculated, so that it is the kind of statistical data we can say. If lead sulfide taken into the consideration, it is having 8 into 10 to the power minus 28 as the solubility product. Solubility product is taken as the KSP. KSP is nothing but a solubility product. Okay. So that solubility product is equal to, so whatever ions are present in this, the product of solubilities of all the ions, whichever present, which is called a solubility product. Okay. So lead sulfide is having 8 into 10 to the power minus 28. HGS is having how much? 4 into 10 to the power minus 53. So 4 into 10 to the power minus 53 is there. Manganese sulfide solubility product is accorded as 2.5 into 10 to the power minus 13. Okay, manganese sulfide is having 2.5 into 10 to the power minus 13 is there. Zinc sulfide solubility product value is 1.6 into 10 to the power minus 24. This is the way you can go for the data only. So it is a kind of question purely given based on remembrance. Okay, so there is no derivation part, there is no kind of a problem solving analogy, rather it is the kind of mapping only. Okay, if you know one or two, so that it is obvious to get what is the correct answer. Okay, lead sulfide solubility product is 8 into 10 to the power minus 28, mercury is 4, manganese is 2.5, zinc sulfide will be 1.6. This is the way you can go with the problem solving for solubility product. This is the question given from chemical equilibrium. Right. Move on to question number 6. Question number 6 again collected from the inorganic chemistry. Inorganic chemistry, and in specific, we can go for it is the kind of hydrates, metal hydrates. The topic is regarding metal hydrates. Okay. Here, the correct statements among the following are: beryllium hydrate and magnesium hydrate are polymeric in nature. So, beryllium hydrate, magnesium hydrate, polymeric or not, we have to identify. Lithium hydride is unreactive to oxygen at a moderate temperature. At normal temperature, lithium hydride, it is in contact with the oxygen or air. It will not show the reactivity inert towards the oxygen. Beryllium hydride and magnesium hydride possess significant covalent character. We have to check it. The stability of alkali hydride follows the order lithium hydride, sodium hydride, potassium hydride, rubidium, and cesium. They are saying increasing order will be there. So let's analyze which are the correct answer. For question number 6, the expected answer is A, B, and C only. D is not correct. Whatever A, B, C mentioned are correct only, but D is wrong one. We have to go for the individual analysis. Why beryllium and magnesium hydrides are polymeric in nature, right? So beryllium chloride is electron deficient. Beryllium chloride is electron deficient since beryllium, two covalent bonds are present. Beryllium halide bonds will be like this. Two covalent bonds will be located. Beryllium chloride has a polymeric structure. In order to make the sufficiency of electrons, it is polymerized. The polymerization because of electron deficiency. Why magnesium hydride is polymeric in nature? Polymeric hydrates are the hydrates of beryllium and magnesium. Polymeric hydrates are large number units joined by hydrogen bonding to produce long chain. Even in the magnesium, beryllium and magnesium, because both are related with the same group, no, so that's the reason why both are having electron deficiency after the formation of hydrates also. Their octet rule not yet satisfied. In order to make the in order to correct the electron deficiency, they get polymerized in the lengthy bonds and they bonded with the hydrogen bonding. So that is the reason why both are having polymeric nature. That is absolutely correct. Option number A. Lithium hydride unreactive to oxygen at a moderate temperature. We will discuss with that. Lithium hydride by no means unreactive towards air. In powdered form, when you are taking a fine crushed one, then only it will go for the reactivity, or else under normal granule conditions, lithium hydride may not go for reactivity towards this lithium, towards the air or else oxygen. Lithium hydride less reactive or heavier, less reactive than heavier alkali metal hydrates. Okay, so to chemist being better able to minimize the reaction surrounding using lithium hydride. That's the reason why lithium hydride is least reactive towards this oxygen. So we can conveniently synthesize the lithium aluminum hydride, sodium borohydride. That kind of compounds can be easily synthesized because of their unreactivity towards this air and oxygen. So that whatever they are saying, lithium hydride is unreactive to oxygen is the correct only. Beryllium hydride and magnesium hydride possess significant covalent nature. So this covalent nature can be explained by the process called Fazan's rules. According to Fazan's, the cationic size will be tiny or else smaller, and anionic size will be larger. smaller cationic size. Larger anionic size is preferable in order to form the covalent character or covalent bond. So any group, if you're considering any main group, from top to bottom, what happens? Size of the atom is gradually increasing, but beryllium, magnesium both are of starting elements only, so that the size of these beryllium and magnesium atoms are smaller in comparison to foregoing elements. Beryllium, magnesium, what else elements you can notice? Calcium, strontium, barium, radium. Such elements will be there in the same second main group. Okay. In comparison to remaining all, beryllium and magnesium being these two are the starting elements, size is smaller, and their polarizing power is larger, so that they are able to form the high covalent nature containing hydrates. But as we are descending down, the cationic size is becoming larger, so that they able to form the ionic hydrates. Beryllium magnesium hydrates are called covalent hydrates, whereas the below group elements like calcium hydride, strontium hydride, barium hydride, radium hydride, all these are the part of ionic hydrates. So that the correct explanation is provided for C only. Let's see in detail. Lithium hydride rather unreactive towards oxygen. That's why we can conveniently synthesize lithium aluminum hydride and lithium borohydride. Just now we completed this session. And according to this is related with the magnesium hydride, beryllium hydride are covalent in nature. Okay, so in order to explain, Poisson rule plays a role over here. According to Poisson rule, cation should be very tiny or very small, and anion will be larger. That is 100% satisfied over there. Beryllium, magnesium are smaller in nature. As far as beryllium hydride, magnesium hydride concerned, magnesium beryl is small relative to high charge ion and the H minus, very large anion. So you will end up with the something that a covalent character. This is the way covalent character is explained over. After this one, stability of alkali hydrides. Lithium hydride is the least stable. Sodium, potassium, rubidium, cesium hydride is highly stable. They are same, but it is not correct order. The order should be reversed. Lithium hydride is only the more stable hydride. Let's explain about that one. Let's see the order of stability. The stability of alkali metal hydrides decreases with increasing the size of metal cation. As the metal cation size increases, its metal hydride stability get decreased. Lithium hydride is more stable in comparison to rubidium hydride. This is because nuclear charge. So compared to lithium, rubidium is having higher nuclear charge. More protons will be there in the central nucleus, so that nuclear power is more. Rubidium nuclear power is more, so that it will strongly binds. It will loosely bonded with hydrogen, because of what metal increases nuclear charge. Smaller the size. Whenever the size is small, what happens? So lithium is a tiny molecule, so whatever electrons are present, so that kind of negative charge can be strongly pulling towards this lithium atom. Because of smaller the size, nuclear power is directly affecting that hydrogen. But in case of rubidium number of protons are more. Nucleus is having more number of protons, so that nuclear power is larger. At the same time, number of shells also increased. The distance between the rubidium central nucleus to hydrogen is longer. That's the reason why. There is a larger distance, lesser the effective forces, so that we can say nucleus is larger, but nuclear charges are weak in case of rubidium hydride. But in case of lithium hydride, we are having the smaller nucleus, and the distance from that nucleus to the hydride ion will be smaller, so that effective attractive forces are operated. Hence, lithium hydride is more stable in comparison to the rubidium hydride. This is the way we can explain this last factor called stability of alkali hydrides. So D is wrong. Apart from this, A, B, C are absolutely correct answers only. For question number 6, option number 4 is the correct answer. By this, we entirely completed the session. We gone with the various dimensions of chemistry, and we solve the various complicated problems, we can say, and authentic sources are taken into the consideration. I am very much grateful for all the sources whoever giving the content which is very much helpful for the examinations whatever they are aspiring for. And I'm sure for your this content very much helpful for your preparation either for entrance or competitive exam as well. These are the questions will be repeated so many times, so that content is but whoever seriously following the content definitely achieve what you are aspiring for. Hence, I'm requesting you to like the channel, comment. In order to get the comment for the session, we have a question over here. So let's have a question for the session. So in the entire periodic table, if you go for, can you please mention the Fossen's rules? Some rules and regulations are there by the Fossen's in order to explain about the covalent nature. Those points are related with the Fossen's rules to be commented in the comment box for the session, right? Share with the aspirants who are very serious about the examination. Subscribe the channel to achieve more updates in the near future. I am very much thankful for your patient listening. Thank you, one and all.